I am, however, a professor of computer science at the University of Illinois, Urbana-Champaign. I'm also the founder of another company called Runtime Verification that I founded back in 2010 to do formal verification. And I'm still not clear whether I'm started or not yet, because I see people in the back. I'm assuming that I started, so here I go. So proof of proof, pi squared, is about generating zero-knowledge proofs from mathematical proofs. So it's zero-knowledge proof of mathematical proof. And this is a foundation, the way we envision it, a foundation for verifiable computing, for what we call universal verifiable computing, because it will power verifiable computing in all languages and virtual machines alike. And the clicker doesn't work. All right, can somebody help with the clicker? All right, now it works. In the process of presenting pi squared, we also want to make an important observation that verifiable computing as it is today is very limited. And we call it verifiable computing 1.0. And what we want to achieve with pi squared is to migrate to what we call verifiable computing 2.0. And I'll go into details what that means. But first, let me remind you some of the limitations of the existing field of verifiable computing, what we call verifiable computing 1.0. It is, first of all, a very fragmented space that lacks interoperability in the sense that we have many languages and VMs for which we do zero knowledge or verifiable computing these days, and we have custom circuits. We even have custom circuits for specific programs, specific applications, not only for languages or VMs. And that leads to this problem of very large, huge trust bases, where we simply have to trust, because we have no other choice, we have to trust millions of lines of code spread across compilers, interpreters, and ZK circuits. Some of the ZK circuits have hundreds of thousands of code themselves that we just have to trust. And maintenance is a moving target, because any language or virtual machine worth its salt evolves. Every few months we have a new version of EVM, a new version of LLVM, a new version of the language. And we always have to keep up with these new versions, with all the circuitry under the hood. And if you are truly interested in correctness, in the sense of formal verified correctness, then we can simply forget it, because that's impossible with the current approach. Because it's very hard to verify even small programs. To verify millions of lines of code, that's hopeless. What we propose in Verifiable Computing 2.0 is to overhaul the entire field. And in what sense? So we believe that we should build verifiable computing on top of one of the oldest and most well-established fields in computer science, which is programming language semantics. The first works in this area were written in 60s, 70s. So what, in a nutshell, a programming language semantics does for us is to reduce systematically and rigorously computation in the language for which you have a formal semantics to mathematical proof, rigorous mathematical proof. That's what we do with formal semantics of languages. Okay, formal semantics, again, allows you to take any computation in the language for which you have the semantics and translate that computation, reduce that computation to a mathematical proof of a theorem that claims exactly what the program was supposed to execute. In the same way, TCP/IP nicely separates the world of applications from the world of hardware, links, pipes, and circuitry. The same way, formal semantics of programming languages allows us to use mathematical proofs and proof integrity protocols the same way data integrity protocols are used in TCP/IP. So we can check basically mathematical proofs and use mathematical proofs as the link between the high-level computations, applications, languages, VMs, and so on, and the low-level circuitry of cryptography. Okay? So in other words, programs, virtual machines, languages, they execute and they generate mathematical proofs, and then we can take the actual mathematical proofs, verify them, check their integrity, and then generate further zero-knowledge proofs that attest for the correctness, for the integrity of those mathematical proofs. And this way we know that the claims were correct. That's what we believe the enabler of verifiable computing 2.0 will be. So how does Pi², our particular implementation of what I said before, work? So it works this way. You start with a claim, and I'm assuming this doesn't have a laser. So you start with a claim that is something that is supposed to be true. Like, this program executed in this state and produced this state. Alice transferred 1 token to Bob, and now Alice has 50 tokens, and Bob has 51 tokens. That is a claim. You start with a claim which is a program in a state in some programming language. But it can be also something more general, like this particular program is correct, or this fact is true. Something which is provable mathematically. Then we can use a framework, language framework, like the K framework, that allows you to extract literally mathematical proofs from that claim. Right? For example, when you execute a program with the K framework, you get a mathematical proof which you can think of as a detailed log of execution that tells you exactly how that program produced the result, to the last mathematical detail. Then introduces a circuit, a zero-knowledge circuit, that is specialized on just checking mathematical proofs, nothing else. So it will take the mathematical proof and check its integrity, and generate a zero-knowledge proof in the end that will attest for the correctness of the mathematical proof that was extracted from the execution of the program that was written in some programming language that was plugged and played here. So if you look end-to-end what you got a programming language and a claim in that programming language, like a program execution, and you got a zero-knowledge certificate, a cryptographic certificate at the end that attests for the correct execution. All right, so this is exactly what you get in verifiable computing as well, except that this is completely independent of any particular programming language or virtual machine. Okay, it's universal. Right, so that's the idea. We started the company Pi² to implement this vision. The company was just founded. We just raised last week. We closed our round, led by Polychain and many other investors. And our mission is to implement this, make it really practical. So I'm going to tell you a bit about our current implementation, and then have a discussion, hopefully. I don't know even how much time I have. I was supposed to have 20 minutes, but since we reshuffled this, I guess nobody can tell me, so then I'll continue. All right. So let me tell you a bit about the baseline. So what we've done, we took some programs in 2 domains that we believe are in need of such a technology, blockchain and AI and machine learning. So we took 2 programs, 2 prototypical programs in this, not large, actually pretty small, and we executed them with the existing ZK-VM technology. So we implemented them in the various languages promoted by these ZK-VMs, and we worked closely with the teams underlying the ZK-VMs. And this way I want to thank all of them. They were very friendly, very helpful to help us implement the best possible checkers using their ZK-VMs. And these are the numbers that we got with the current state of the art. So with risk 0, for example, if you implement ERC20, you expect these numbers for a transfer, these numbers for a batch transfer of 5,000. And so as you can see, the exact numbers don't matter here. What matters is that we are in the order of seconds or so to execute even small programs, okay, and generate ZK proofs for them. I know that Cairo now has some amazing new results that we are looking forward to trying soon. Right, so that's the state of the art. This is what we are trying to make correct and also improve, hopefully, in terms of performance. So this is what we've done. So what we see here has nothing to do with our approach, pi squared. This is what happens right now. And this is what we've done. We implemented our proof checker here, currently in just one of these ZK VMs in risk 0 to see what we get. And actually, we have several other implementations going on, but I will only mention one, the risk 0 implementation. So we implemented this in risk 0. And why we've done that? Because that's the cheapest way for us to get ZK proofs here from mathematical proofs. Okay? So it doesn't matter how you implement your proof checker as far as you get a ZK proof that is verifiable. And right, so now let's take the same programs, let's run them now with the semantics of the programming language as a mathematical proof, generate the mathematical proof, verify the mathematical proof, generate the ZK proof, and let's see what we get. All right, so we started about a year ago, and we got nothing because the mathematical proofs were so huge that it was hopeless to run them through these the ZK VMs. But there is something really nice about mathematical proofs, which, if there is one thing that we can take home from this talk, I hope that could be the thing. Mathematical proofs can be engineered, right? Many of you probably have seen mathematical proofs which are ugly for a result, and then mathematical proofs which are beautiful, nice and compact, okay? We can do exactly the same thing here. So that's what we've done. We took these mathematical proofs that generated automatically blindly by the framework from just observing the execution of the program, and then we engineered them automatically to make them smaller, more compact. You can extract lemmas. If you have a loop, for example, right? You can extract the entire loop as a lemma, and now each time you execute the loop, you just call the lemma instead of executing all the statements. And you can make the mathematical proof much, 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 much smaller. And not too long after that, we started getting some numbers, feasible numbers, and a few months later, oops, there should be one more column here in December. All right, anyway, so the numbers that we got here now are within an order of magnitude or so, right? Larger than the best of the best. This is what we get, again, running the programs directly with the ZK VMs, and this is what you get taking them through the entire mathematical framework, where everything is correct by construction. You don't have to worry about correctness anymore. Everything is correct, but the price to pay is that they are 10x slower. Okay? So our mission is to make this much, much, much faster. Okay? We want to implement a circuit for mathematics that will be much faster, because this is not the way to go. The way to go is not to implement the proof checker in a particular complex already ZK VM, but instead is to have a circuit for mathematics directly. And a few words about the current progress. So we started working on our own circuit using Circom. Feel free to contact us. We can give you access to the program and play with it. Essentially, this allows us to specialize the ZKP generation to mathematical proofs. And there are a couple of innovations that are really, really interesting in terms of how we connect mathematical logic with cryptography that have not been explored so far. It's interesting. If you look at the two communities, verifiable computing and formal verification, or programming language communities, both communities aim at the same thing, more or less, correctness of program executions, but using completely different methods and orthogonal. These were developed by cryptographers. These were developed by formal methods people. So now we can bring them together very, very nicely. And one of the ways that we started looking into that is how to get fingerprints for actual mathematical formulae, right? And there is a nice way to turn mathematical formulae, like this, into polynomials. And then we can sample those polynomials in random numbers, random inputs. And now we can associate actually a number to a mathematical formula. So it doesn't matter how big that mathematical formula is, with a very, very high precision, you can, probability, you can identify it uniquely with a number. Okay, this is the first step. And this is also compositional, homomorphically, in the sense that you can generate fingerprints of combined formulae-like implications from the fingerprints of the parts. That's one important component. And the second important component is that we can take now mathematical logic reasoning steps, like modus ponens, right? Modus ponens where from alpha and alpha implies beta, you can derive beta. If you prove alpha implies beta, now you can also derive beta. So this turns very nicely now into cryptographic artifacts. So basically, we can combine these fingerprints and that I mentioned for formulae, and then you can check mathematical steps like this using very basic cryptographic operations like subset, like multiset, for example, subset checking, or membership checking, and all these are very efficiently implemented cryptographically. So we believe that this interesting relationship between mathematical logic and cryptography will allow us to make things really elegant and fast. It's all also very parallelizable. So after a few months of experiments using this approach, we improved already the performance more than 10 times by simply implementing the circuit, bare hardware, to say so, cryptographic hardware. Also, one other thing that we noticed, and if there is a second thing that you can take home from this talk, this would be that, namely that mathematical proofs are embarrassingly parallel to check. Okay, what it means is that if you have a mathematical proof, which can have a billion steps, doesn't matter how big it is, that proof is true, if and only if every single step is true, and you can check every single step completely independently and in parallel with all the other steps. Okay, so this gives you an embarrassingly parallel ZKP generator for integrity of mathematical proofs. And we did some experiments, played a bit with that, and that will improve the performance, at least exploiting this parallelism, another order of magnitude. And finally, and most importantly, you can do a lot of magic with mathematical proofs that you cannot do directly with cryptography in verifiable computing. You can massage mathematical proofs. You can have long and ugly mathematical proofs and redo them pretty much automatically into small, elegant mathematical proofs. Additionally, if you combine formal verification with this approach, then formal verification can actually make proofs much, much smaller and faster to check. Here is an example. At runtime verification, we formally verified Uniswap. And one of the things that you prove about Uniswap is that this function, which has a loop inside, calculates the square root, unit square root, right, in Uniswap. And you do this formal verification once and for all. You prove mathematically a theorem that says that this code implements the square root function. Okay, now, each time I call this function, suppose that I call it on 100, square root of 100. Square root of 100, I can give you the result 10 immediately in constant size mathematical proof. I don't need to run the loop because I already proved what this program does. I already have a mathematical proof that square root of 100 is 10. I don't need to run the program to give you a proof that the square root of 100 is 10. Okay, this is unique to this combination of mathematics, formal verification, and cryptography that you cannot get from just cryptography and verifiable computing. You need to go through this. And this is another area that we plan to explore in depth. And with this, I'd like to close with our vision for the future of blockchain based on pi squared, which is that decentralized networks powered by pi squared can be and will be universal. The programming language does not matter, should not matter. Okay? What it means is that you can plug and play your language. Your language is a mathematical theory, a formal semantics. Once you have that mathematical theory, just store it somewhere, settle it somewhere on the chain or some address, Java, C, Solidity, EVM, Rust, WASM. All of them are mathematical theories. Once you have them, now you can take computation done with these languages, and those become claims that have mathematical proofs that now you can check using the same circuitry, the same validation mechanism for all, the same circuit for all languages, all computation in all languages. And more than that, you can actually settle the entire mathematics, science, mathematical theorems. All of them can be settled with exactly the same technology. And this way, we'll have universal settlement of computation in all languages. And programs will never need to be re-executed. I don't need to re-execute a program once I have a proof, right, of the execution. Only need to validate, verify proofs. And yes, everything will be correct by construction and interoperable as well. Interoperability is not even an issue, it's obvious. In mathematics, you use a theorem proved by somebody else in your theorem. You don't call that interoperability. That just happens by the nature of mathematics. The same, you get interoperability for free here. And with this, I'm done. Thank you.